Good evening, everyone. So, there are many new faces here. So, I think I should introduce myself first. So, I am Abhirup Karmakar from Astrophysical Sciences, 4th year BSc student. And as you all know, today I am going to discuss string theory. But as you know, the title is string theory for maybe, but I don't know that this will actually be for babies. So I just leave it for you to decide at the end of the talk. So as you all know that the string theory is very fascinating start. From childhood we all heard about string theory and all the stuff. And so today I will discuss mainly that why string theory is so much famous. So I will be rigorous in sometimes, but I will mostly be qualitative. So let's start. So what basically string theory does? So string theory basically unifies two known ideas, that is, one is the standard model of particle physics and another is gravity. Now, what is standard model of particle physics? This basically includes three fundamental interactions like strong, weak. These are linear interactions, and another is electromagnetic. But unfortunately, gravity is not a part of standard model. So this is very much absurd thing. But what string theory does, it provides a beautiful description to unify both of the ideas. So what string theory does, string theory basically unifies the standard model interactions, mainly strong and electromagnetic forces, with gravity. And as you know, these are all quantum theories, right? So these are all quantum theories, but you know, gravity is basically classical, which until now, like Newton proposed is universal law of gravitation, and then Einstein modified that. But all these are classical theories. So in order to unify standard model with gravity, we need to convert it to some quantum theory. That is the first requirement. And in order to do this thing, there are lots of problems. But I will not go into that problem. So basically, we need to develop something known as quantum gravity. Then only we can combine these two. Now, so basically, string theory. What is string theory? String theory basically is one of the best candidates for quantum gravity. Base theory of quantum, base candidate of quantum gravity. There are others. So, in order to define or construct a quantum theory of gravity, we must know what are the fundamental constants involved in quantum theory of gravity. So, it is very much obvious that fundamental constants should be A star, that is coming from quantum theory, any kind of quantum theory. Another is C, that is the speed of the light. Another is Newton's gravitational constant. These are the most basic. Now, these constants, as you all know, these are dimension 2 constants, and we can combine them to make one length scale, one time scale, and one mass scale. And these are historically known as the Planck length, Planck time, and Planck mass. So it is very easy to do dimensional analysis to get the form. So if you do that, you will come out with mass. Now, why these quantities are important? Because these are the obvious length scale, time scale, or mass scale that basically governs the quantum gravity region. So roughly, if you put the values of these constants, this will come out to be 10 to the power minus 33 centimeter. This is 10 to the power minus 44 second, and this is 10 to the power minus 5. Now, we all know about LHC, Large Hadron Collider, that it probes the smallest length to different scales, like at the level of quarks. That is roughly 10 to the power minus 70 centimeter. Roughly, okay. So this is much smaller than that. So if the fundamental particles are excitations of a string, we cannot see the stringiness because of the length. So that's why we see them as a particle up to now. So the length scale is very much small, as I discussed, as compared to the current length scale that we can do. Now time scale. So this is an extremely small time. So quantum gravity will be effective when the universe is this much time away. So quantum gravity can be important in two scenarios, that is in early universe, and there is another thing, that is we know Einstein's general relativity, but that breaks down as large gravitational or extreme gravitational scenarios, like singularity of the black. So in that scenario, there is some singularity, but these are essential singularities of Einstein theory, and Einstein theory cannot explain this. So we need quantum. Now come to the mass. This is very much crucial.
Are you sure that time scale analysis, or how does singularities correspond to that?
No, this is not corresponding to the singularity. I am just talking about that at the singularity. Einstein theory fails at the singularity. So that's why there it says that maybe some quantum gravity effects can be there. Yeah, so the important thing is the mass. There is a Planck mass. You can see it is 10 to the power minus 5 gram, right? But we all know mass of the proton. Mass of the proton is, I forward the mass of the proton. It is like 1 kb natural unit to forward. Okay. So by t square. So if you convert this to gram, we can see that mg is roughly 10 to the power 19 times the mass of the proton. Now this is one of the absurd things. Why? Because if our physical theory on the theory of the nature is based on these three constants, then why mass of the proton is so much large in compared to the obvious length, means obvious mass? So this is one of the absurd things, and this is known as the hierarchy problem. In a very crude sense. Because hierarchy means there is a hierarchy of mass, right? So all standard model particles mass are very much less than the obvious mass.
Mt is the mass of what?
Mt is the obvious mass scale coming from this constant.
Why are you comparing a mass scale with mass of particles?
Because if our fundamental theory is based on these three constants, because this is an obvious mass, or means the fundamental particles should have the mass approximately like this.
Why?
I mean, this is a puzzle. I mean, this is basically one single mass scale should be there, a fundamental mass scale.
Why? What is the problem with that?
Yeah, this is not the case because there are four fundamental interactions, right? But why four? So this is also why four?
No, we have measured it to be.
Yeah, but what string theory does, it actually combines all the interactions to a single interaction. It unifies. So basically there should be only one mass. That is the problem.
What would be the problem if this is not the mass?
I don't understand.
Like you are saying that this would be the proton's mass is like much different order of the what would be the natural mass. Like, what is the problem if we don't like it doesn't come to be in the natural scale?
No.
What
I understand the
normally
problem.
doesn't cause it the theory?
No, understand the problem. First, the proton mass coming from the strong direction, right? Then why the fundamental constant limiting the mass scale is so much larger than simply comparable in some sense.
Why should it be comparable? This is what I do not understand, because if you consider, let's say you consider weak force,
Yes.
okay, and you have many particles in weak force.
Yes.
All of the particle masses are,
All of the particle masses are like in G.
they turn out to be comparable. Fine. Why do you expect the same behavior when you include gravity?
Yeah. So all the theories are quantum theories that you understand, right? All are relativistic quantum theories. So H pattern C should be there. In first place. So when you include gravity, means G, you see that NV is coming out to be very much larger than that. So this is a problem, right? I mean,
But in this case, like, why do we expect that scale to be of the order of
which one?
like the LP that we are getting? Why do we expect that scale to be near the order of the particle?
Okay, we can go up to this order. Yeah, that's good.
So if I have understood the problem correctly,
Yes.
you have taken aspects from classical theory and quantum theory, right? And you have combined them to create some lenses.
Yes.
And then you want to find a physical meaning in them. So you want to assign that mass, which you have constructed by combining a classical and a quantum theory
Yeah.
to a known particle.
Yeah, basically what we want to build a quantum theory of gravity. So these three should be there. These three fundamental constants.
So if I take out G,
Yes.
I can still construct some mass scale with H bar and C with appropriate dimension analysis, right?
Okay, maybe. But I
Does
don't
that? Okay, so does that? My question is precisely that. So does that turn out to be G V per C square?
Okay, we can see that side of the term. Okay, so this is like a hierarchy puzzle in the sense that I have already told that there is a very much difference between the obvious mass scale and the mass scale we are observing right now. Okay, so to resolve this issue, we need to introduce. Okay, I don't know this is the only resolution or not, but one of the resolution is to introduce extra special units. So we have 4, right? 1 time and 3 special coordinates. These are all infinite extent, but we want to add some extra special units. show what is the motive behind this. If we add some extra special dimension, we can show that the fundamental mass scale becomes the mass scale of this MP, but when you try to cast it on 4D, you will get this mass scale. So basically this means resolve the problem in some way. So this actually means our whole world is basically a higher dimensional world, and I will go into that. So basically there is a relation, I will not prove it. If you calculate the gravitational constant in d space-time dimension with the basically the ratio of the two, the gravitational constant in d space-time dimension by d4 dimension, that is basically the volume of the compactified extra dimension. So what is meant by compactification? I will just come in a few minutes. So basically this is the volume occupied by the extra dimension. Okay, so this is actually not needed much, but what I want to say that there is one experiment which the electromagnetic experiment that basically rules out the extra special dimension in some way. How? If you have a point charge plus q, so it will, the electric field lines will be radially outward and the electric field goes as 1 by r, right? But if you introduce extra dimension, then this electric field will go as r to the power e minus, where our space-time dimension is d plus 1. 1 is time and d is our special dimension. But this is well tested up to this length scale that 1 by r square is valid. Then how we can say that d is greater than 3 for us? So basically this rules out the extra special dimension theory. But then we devise another thing, very much interesting question.
Is the artificial dimension now coming from the column?
Yes, it will come from the Gauss law in higher dimensions. If you apply the Gauss law, we have to use this volume of s d minus 1. So basically this is the sphere of d minus 1 dimension. That is kind of short.
Don't write that.
Okay, it will not be. So you have to just substitute this. So there is one r also. Something like that. From that you can get the electric field d plus 1 space dimension. Okay. So what is the resolution? Like, as you can see that it basically rules out the extra special dimension. So we have devised a very interesting thing, that is, like, for example, imagine ID perspective. How you can imagine in board we cannot. So let's just think about 5 to 3D. And there is some line where it is. So basically this direction is the extra dimension. And these are the 4D hypersurfaces I am considering. So these are the, like, you cut a cake, right? The surface is like that. So what you do, you say that these are 4D slices of height. Okay? So these are called branes. That's what comes from main brane. Okay? So these are like branes, and you propose that all electromagnetic field and all standard model fields are confined to this 4D plane, and they do not come out in the extra dimension. Then the problem is resolved. It is not always.
No, but if
the electromagnetic force does not go in the extra dimension, and we introduce the extra dimension so we can take care of the forces. And
Yes, yes, I will come. So only the standard model interactions around the 4D spatial hypersurface, and gravity can move in the bulk. So how it resolves the hierarchy problem? So actually standard model interactions are strong as compared to gravity. We know gravity is weak in our universe. But when you say that gravity can propagate in the bulk, so the whole space-time is called bulk, and these slices are called brain. So these are terminology. So in our universe, gravity is weak, right? So why is that? The gravity is as strong as standard model interactions, but there are small fraction is only contributing in the sense. That's why it's weak in our universe, but it is not weak fundamentally.
sorry.
So what I am saying, the standard model interactions are confined to the brain, right? But gravity can move in the extra dimension.
I didn't understand one.
Yes.
What do you mean by gravity can propagate outside the brain? And yeah, what does it mean to you?
How can I explain? Like this is a very crude way of explaining. So basically, what you assume that all your standard model interactions are confined to there, but gravity is not. So I think a simple way of dealing with it right now.
So is it that if I keep my calculations confined to a 4D brain world scenario?
So we will experience weak gravity.
Okay.
So why gravity is weak? Because gravity, the most contribution of gravity is in the bulk, very less is in the brain.
Okay.
You can think of it in a very crude way as you are missing out a lot of flux.
Yes. So if you write a graviton wave function, just that you will see it is very much lower here, peak somewhere else.
Okay, is there specific movement tendency that the peak in the wave function can occur in the brain?
Yeah, it can occur in the brain. Okay, I will not go into that. There are many models actually, string-inspired models that actually says that there are two brains. So this is a two-brain scenario. You can see two brains I have drawn. So one of the brain we are living, and another brain we are not living. So the gravity is like peak here, but not peak here.
So it can never be that gravity can peak anytime soon in our universe.
No. In that model, of course, I don't know.
So in that sense, the gravity there would be pretty strong.
Yes, there will be pretty strong, but not yet. So very weak. Tail is there.
Just one question. What is the cause of asymmetry?
What is the cause of the asymmetry? No, you constant like that, right? To resolve the hierarchy problem.
But also like in this case, gravity is traveling in the bulk and the other forces are not. So there's a asymmetry there. You will
Yeah, but this is not like a fundamental asymmetry because you are constructing your theory like that. You are defining like that.
I think what Ranjan
Yeah,
wants to
I
say is
understand.
there has to be some way in which you can explain the confinement of the standard
Yeah.
model particles
Yeah.
in the brains.
Yeah, it can be actually. So basically, various brains are intersecting in the string theory, and the standard model interactions are produced. And as far as I know, so this is very a simple model. It is not the whole thing.
How can we say that in the fifth dimension only the maximum gravity is present, and is it somehow experimentally proved, or is it just an assumption?
It's a model.
Only an assumption.
It's a model, right?
If you want experimental proof, then you should go to that other brain. Where gravity is
But we cannot leave the 4D hypersurface, right?
Yeah. Unfortunately, we are made up of standard.
Yeah, because we are made up of standard model particle. How can we go into the essence?
What is the magnitude of VC? because since you are proposing this, then the magnitude
Okay,
will be
it
one.
depends on how many extra dimensions you have. Depends on number of extra dimensions.
So say for 5%, give me a number.
Yeah, actually there is a formula. It is like something like 2 pi times r to the power n, where n is the number of extra dimensions.
And R is
R is related to, I guess,
radius of the toroid.
yeah, radius of the, I guess this is a free parameter. Right?
Is it a question?
It is a free parameter. He just wants some number for.
Yeah, I can give you reference later.
There's a question from
To the knowledge audience, is there any difference between a hypersurface and a plane?
Yeah, there is a difference, and I will come to that. Now you can see that it is a fixed height dimension, right? So you can cut it like all the. So what is the uniqueness to define a plane? So I will come to that.
I had a question,
Yes.
like regarding that VC only, that VC. So it's, you are saying it's a volume of the remaining.
Remaining dimension.
Yeah. So is it like the volume we see in everyday, like the 3D volumes which you see, or it has some different units or manifestation?
No, it doesn't have a different unit, right? You can see that R is of the length unit, so it is just.
So it's like meter. You can use meter cube to define, means quantify it.
Not meter cube, that will depend on the number of
Number of
dimensions.
extra
Num-
Depend on
oh, okay.
This is just a schematic way of writing. The exact.
Okay.
I had one more. As you said, there would be some wave function which will peak at the middle of this, where the gravity will be maximum. So, do you have any such example of function? I mean, whatever you are saying, do you
Any
have a
function?
function to prove this?
Yeah, Bessel functions. There is Bessel functions in the Graviton wave function. Right. Means you are saying that what function is used?
Wave function of the gravity.
Huh? Yeah, this is exponent, but Bessel function is also there. So this is a complicated. I can send you references if you want to see what the Graviton. So basically, the Graviton wave functions set anywhere same sorting way. Okay, so now how to uniquely define the branes? So basically there is a recipe to now see where should I define the branes? There should be two fixed points, like one fixed point. Now forget about, let's say one brane. So you need one fixed point to define the brane. Why? Because you need a stable configuration. Brane should be a stable object. Okay. Now how to generate the fixed points? Now to generate fixed point, we need to know two things. That is, first thing is compactification, is how to compactify the extra dimension. And then we need to know something known as orbital volume. So very qualitative describe what are these things. So compactification is very simple. So like you have a line, okay? Real
I
line.
have a question. So, the planes you have considered, like they are planar.
No, they can be carved also.
So it is a curved plane. Then how do you describe then the distance will vary, right?
Yeah, distance will vary. So basically the distance between these two branes is a function of the coordinates of the plane. Where you are.
What changes will you what changes in the theory will
So
you-
we have to define a metric here also. So you have a global metric, some global G unit. Now you have to project the metric in the brane. So you get a inducement. So metric is something like those who not know. So basically metric is something you measure the distance. Okay, so suppose you have a real line. Now you want to, real line means 1D, okay? So suppose you have a one extra dimension. Now how to generate fixed point? like okay, no. First of all, I am saying the compactification. How to compactify the extra dimension? Like for simple thing, like you need a periodic thing. Like so, suppose 2 by r, some positive number r, and you say that this repeats after 1. So basically, you identify one point. So the resulting base will be circle with a radius.
Why does it need to be periodic?
No, I am just saying. So this is a circular compactification. There are many compactifications in one of them. So this is circular compactification. There can be other compactifications as well. So these are just examples. So another can be, suppose you have two extra dimensions. Okay. So x, y are the coordinates. So you identify something like this. So you do a identification, periodic identification of the y coordinate. So the resulting space will be cylinder. Right. So this will be the x direction. This is the y and radius is r. So this is a cylindrical compactification. Now if we do both of them to be periodically identified, right? So your compactification will be a toroid, right? So you basically has this.
So, I have a question.
Yes.
The compactification is a sort of homeomorphic function.
I don't know.
I mean, the thing is,
Yes.
you are changing the actual space, right? You are essentially defining a function for one point or the
So this is an operation. This is called the identification.
Yeah.
So this operation is called the identification. So there are definitions. So I am not doing it. I will send you the definition. So this is called the toroidal compactification. Okay. So these are the compactifications. And now how to generate fixed points. Right. So for fixed point we have to identify. So in this three compactification there is no fixed point. So what are the fixed points? Fixed points are something that are identified with themselves. Fixed point is something like A is identified with A. Then A is the fixed point. So I am trying to. Suppose you have a 1D line, right? Then what you do this identification. Means all negative x's are identified with plus x. Then what is the resulting space? The resulting space will be this one. So only this one. So you see 0 is identified with 0 under this operation. Right? So you generate a fixed point here. Now you can define your brain. So this is and this.
There has been a question on what is the difference. Is there any upper limit to the number of extra dimensions that?
Yeah, experimentally you can put bounds on that. Like there are some models like large extra dimensions. From there you can get some bound on the number of extra dimensions from the current experiment because we have detected any extra dimension. And you can see that 0 is identified with 0 under this identification. So 0 is a fixed point. So this is the definition of fixed point. And you can define your brain here because it is fixed. So there is no vibration of the brain in the compartment. It is stable configuration. Right, so
Now
this
there is a comment from
yes.
but those bounds are on the size of the extra dimensions.
Yes.
But
There
there
are
are
for
the
numbers
size
also.
also.
As far as I know, number of extra dimension is also bounded. Now, this is mainly for large distributional model, not for large in the sense. Right? There are some models. Large in the sense, means not very much small. It's like micrometer range. That is a large.
So basically there are no model independent bounds of these.
Everything are model independent. What model you are considering? Okay. So this operation is called Z2 operation. So it is a carry change minus x to x. And this resulting space is R1 Z2 R2. Is working on this R1 Z2 R2.
But over here you can only have one brain, right?
Yes, only one. Means only one fixed point. So we
No, you can have another brain that has to get integrated.
Yes. Yes.
How does that come?
Right now deriving means there are some range fluctuation. If you consider fixed point, then the fluctuation will be zero.
Oh, no, you're right.
At fixed point, the fluctuation is when you are
Correct.
it will be stable. It will be stable fluctuation. Now there are another very much famous folding that is S1, S2. S1 is circle. So if you have any circle of radius R, you generate a fixed points. What you do, you identify the upper plane and lower plane. Identify, and the resulting space will be something like that with two fixed points. So you can say this is theta equal to 0, this is theta equal to pi. And you define your two branes there. So this is S1 Z1. And there are some models, string inspired models that actually I am working on. These are called random Sundra models. So where basically you would have these two brain kind of scenario or one brain kind of scenario. And this actually solves some of this is a model of course. So this resolves the hierarchy problem. Now question comes, why we can't see the Excel? Right? So for that I will describe a very crude way of explaining the things with very toy example. There is a square. It's 1D square. Quantum. Non-relative quantum mechanics. So you have something like this potential. Now forget about all this. This is like here. And these are infinite. And VD is 0. And we all know the wave functions, right? Very much. Where n is from 1 to because n equal to 0 is not allowed because it doesn't mean anything. And these are the energy items. Take a stereo. Now what I do, I introduce one extra dimension over this 1 bit square. This will take a lot of time to derive. No way. Now what I do, I Oh, one important thing to derive this wave function is you need to impose the boundary condition. That is very much important. That is your wave function cancel as the extreme. Now what we do? Construct something square wave with one extra term. Okay. So suppose x is our original quantity and y is the extra term, and you make the identity, the cylindrical identification. So what we now have a cylindrical space. This is the radius r, and this is the length of what? So your particle is now moving in a circular space. And what you assume that this radius is very much small. So it is very small extra dimension. It is completely high, and it is very much less than the length scale of the problem. Now, what is the Schrodinger equation in the cylindrical surface? That is very much simple. This is the Schrodinger equation, right? Now, how can you solve this? Just do separation of variable. Some psi x, phi. Right? Now the important thing is, now if you do this separation of variable, there will be two equations. Right? I am not writing the two equations, and you have to impose the boundary conditions. So psi of 0, psi of a. This is one boundary condition, and what you have to do, you have to apply the periodic boundary condition on phi. Okay. If you apply these two boundary condition, you will get the solution of the wave. The solutions are same for this one. You get some phi L. Important thing is n is starting from 1 to okay, and but L can be from 0. Now, what are the energy eigenvalues? So you put these solutions there and you get the E, total E. This depends on n and E. Right? Now see that as L equal to 0 is allowed, you can put L equal to 0. What you get? You will get the old energy level, right? When you have only one unit cell. But you can see that other values of L's are also possible. So there are extra energy levels. So as you introduce extra dimension, you get extra energy levels. But all energy levels are there. On top of that, you have other levels. Now, what is the lowest new extra levels? So that is n equal to 1 and n equal to 1. These are the lowest mu levels. So those are the old levels. So I am saying the first new level.
First new level include F can be 0.
If you put n equal to 0, all will be old levels.
Okay, okay.
All will be old
Like
levels.
except
Except the
except of the old.
yes. The first new level will come if you put n equal to 1, n equal to 1. So
But that is not the ground state.
no, not now. I am saying the so I am just I will draw the energy. So
This is the oldest for the non-extra dimension.
yes, yes. When you just consider one extra means only one dimension, not all dimension. So if you introduce extra dimension, compactify very small, you get there is more energy levels and
What if we have n equal to 0 and l equal to 1?
It cannot be
N cannot be
n cannot be zero.
Yeah,
So this is the new energy level, first new energy level. Okay. So this will right. Now see, I have compactified the extra dimension very small as compared to the A, right? So basically, you can approximate it to this.
This is why did you consider that?
Because we cannot observe the extra dimension, right? But we are considering very small extra dimension as compared to the length scale of the original dimension. So if you consider that, then this part is negligible, only this part will be dominant. And you get. Now, what you do? Suppose we don't know the extra dimension thing, we only know this. So when the first new energy level will come, so we basically compare this expression with that new level to get a feeling of what n value the new energy level will come. So basically what I am saying, you just equate this and this. So you will get an n. At that n you will get the new level. So this is the new energy level, right? Suppose we don't know the extra dimension. We only know this. So now if we somehow equate these two, we will get the effective n value for which the extra new level will come. So if you do that identification, ultimately, basically you equate this expression with this one. Right? If you do that, you get n is coming out to be a by 5, right? Now you have considered r is very much less than a. So this is very less. So if you draw the energy levels, the known energy levels like this, these are new energy levels. So we don't have equipment to measure this. Our energy is, we have low energy there. Our probing energy is very much low right now. So we cannot go the action. That level is very much higher on our current ability to measure.
Like different ones, what is the order of magnitude?
Yeah, you can see from here.
Yeah,
So this is a very crude example. This is not the right thing. It is just a for a feeling. What is happening.
You can just tell him the greatest energy at
Yeah, means whatever the center of mass value of the LHC right now, that is the bound. Because we have not detected anything. So right now it is like 13.5 TeV. So roughly around that. So this actually provides the, it actually gives the feeling why extra dimensions are given from the current experiments. Is there any question? will go to string. So how much time? What are half an hour. So why we consider strings, right? So till now I have not talked about strings, right?
If the energy level is so much tremendous and it's not something which we can prove, then until we find somewhere around, isn't the theory doomed?
Yes, I will
How really should you at least have some thing to it?
see.
You either
What I believe, this is my personal opinion. That, to study string theory for experimental calculation, I think it's not right to study string theory for that.
then it's not physics, it's maths.
For mathematical, because that theory is very much mathematical.
theoretical, no, but mathematical physics is
There is something very deep here which you need to
Because
understand.
this is the best theory out there, right?
No, even if you assume it not to be the best theory,
But it will be
any
something like
theory
that.
which combines quantum theory and gravitation will have those three scales which you saw at the very beginning, and you can see that all those three scales are unachievable. So no matter what theory you are doing to explain quantum gravity, experiments are very different.
But there are other experimental derivation, like from cosmology perspective, not from the collider physics that can.
Right.
But
So
I don't know.
observations,
From
very early universe observations.
like from CMB or something. But I don't know the experimental details. Right? So the question is why strings? As at the beginning I have said that strings can combine standard model interactions and gravity. So I will give you a flavor how it does. So basically, when you solve for various configuration of strings, you will get mainly two types of string. One is open string, and another is closed string. I will actually solve it for this. Don't worry. I'll just come to. So what actually open strings are? All standard model excitations or interactions or standard model particles are open string excitations. Now you can see the open strings have endpoints, right? So open strings have two fixed endpoints, and this is somehow related to the D branes. Means branes I have talked about. So when you have two branes, or one brane can also be. So the two fixed points is connected by some string. So when this string basically oscillates, it produces the standard model interactions on the brane. And why? And now what closed string does? Closed string is basically graviton. In closed string excitations are graviton. Closed strings doesn't have any fixed point. It will move around the path. It is not confined to the brane. So I will come to that. So basically the spectrum of string theory contain both the open string vibrations and closed string vibration, means standard model and graviton. Means there is a mass. To be precise, there is a massless thinking. That is the main main amazing thing that happened around 60s or 70s when theories found that there is a massless thinking mode in the string spectrum. That's why the sensory becomes so much dense.
How do they respect?
I will give you a flavor of how it is.
And one question is that for an open string, why do the ends have to be fixed?
because there should be two endpoints of this open string. Yeah. It should have always. Like if you consider a guitar string, there should be two endpoints.
Yeah, endpoints fine, but why does it have to be fixed?
They may not be fixed. I will come to that. Like they can move around. Right.
But
If this is fixed, right, then you have a D brain.
identified with that.
So that is called the D0. So brain has 0 dimension. But if the string means endpoints can move around this brain, so this is 2 dimension, right? So this is D2 brain. So considering that there can be many possibilities.
If it moves around in 3D, then it's 3D.
Yeah, so you said the graviton is like the closed string, can be related to closed string vibration. So in the beginning of the lecture, you pointed out a Bessel function like structure, of the like interaction of the graviton. So how can this be related to this closed string vibration?
Yeah, means now mathematically I guess we can show that. But for that was just a model. That was pure string theory. This is string inspired model. And for string theory you need to do detailed calculations for this.
Yeah, oh.
Now what I do, so we will study some non-relating string. Classical.
One question.
Yes.
So like you are saying that this in the open string that both the end of the strings are actually telling us where the brain is placed.
Yes.
So if that is the case, and you are seeing the vibration of one end of the open string is telling us where the standard model particles are. So what is the other end of the open string telling us? Like, how can you say that the standard model particles are actually confined to one of the brains?
Okay, I don't know the exact construction. There can be many constructions possible. I just give you one model construction. That is for one brain getting standard model interaction. Many possibilities. Right? There are interactions of brains. In one brain intersect other brains. Like that. There are many kinds of it. I also don't know.
One question. So, if we consider the open string, we always have two open ends, right? So, does that mean that there will always be two pair of brains
To
together?
answer your question, it can be like that. Suppose two brain, but our string is like.
So then the idea that the both the like the end of the strings are telling us where the two brains are, that is not.
No, it may not be two brains, it can be one brain also. Meaning attached to one. It can
So the
be-
end are attached to one of the brains.
But it can be free as well. Like if you have something like box and you have open string, like in the room if you have open string, it will move around, right? So this is also a brain. The whole space is a brain. That is called the space between people.
So when you are saying that the strings are attached to two brains, like two separate brains, then the like that is a very great question. I don't know, that's why I'm asking. Then it should somewhere be related to the difference in the distance between the two brains, right?
And maybe yes. Yes.
So what is the like? You said that we know the difference between the distance of the two brains. There are various models like that, right? So in that case, will that be equal to the first length scale you get? So that will be equal to that one. Wait, did you understand my question? It's a very great question, but
Okay, I will think about that.
What is the need of this? I think that
yes, yes. Like in the simulated case, like we told that MP is related to.
It depends on the
Various
model, I
models.
guess. It depends on what model you are considering. If
Then-
you are considering a two-brain model, the distance between the two brain will come to the. So in order to solve the hierarchy problem, what parameter actually you need?
Then how
Yeah,
is this a
actually.
fundamental theory?
Rather
If it is dependent on
modeling
models.
and reason.
Yeah, I mean, there can be very much possibilities to compact differ, right? So that is the one very important question, because in string theory we have different solutions, different compactabilities. There are many solutions.
Can you give us one length scale for one particular model? That would be helpful for us.
I will check that and I will check. So right now, okay. So non-relativistic classical strings.
One question I have.
Yes.
What is a string?
What is that?
String? Because I don't think string is physical here.
Yes.
Because it would have been you would have to measure it. So what's a string then?
Strings.
What is it? Because the entire construct is in, I think, in a functional space. Then what is the string here?
Okay. So right. String is.
That cannot be right. It's not physical. Then if I
So what is the point partition?
Yes.
what is the point partition? What is this like modern? I'm asking you, right?
No, I'm giving you a sense of the position of this question.
Point particle will be defined as something whose mass is tending to 0 by, and spatially
Point particle is nothing but the mass.
so okay, so basically whose dimensions are converging to something 0.
But there cannot be any such weird thing, right?
Yeah, but you have a point mathematical particles.
Yeah, so the point,
I guess this is just
the
a
point is also not
construction.
physical.
Yeah, right, but this is also not physical.
Yeah, so that in that same sense,
Yeah, but
so
point has a mathematical definition. Zero dimension thing is a point.
string is a one-dimensional.
One-dimensional
What's the definition? It's just one dimensional. That
Yeah,
is
it's a
Yeah.
one-dimensional object.
One. So if you consider a one-dimensional line, and there are many point particles on it.
It is still not dimensional if you choose its curve.
What exactly is the object? It's a wonderful object.
We need some two questions. Spatial coordinate with string and string in that regard, right?
No, you need one coordinate.
For point particle, you need only one parameter to specify curve and space. But for
No, for a string, for any
For a string,
one-dimensional object,
you need two parameters.
how do you need two parameters? When you
Because this is
embed
a
a
one
string, when you embed a string into some high-dimensional space, then
Yes,
you need two parameters.
Yes.
But just to parameterize a string, you need only one parameter. You need a starting point and a proper time kind of a coordinate.
Yeah, I
So,
understand.
Spatial it is one dimensional. String is also one dimensional.
String is one-dimensional. It can
So
be
you are
embedded
saying like
in
a static
any
string.
number.
For a static string, you are saying. For a static string, you are saying.
Whatever it's static or dynamic.
I think you need two parameters.
As long as it's a one-dimensional object, it can be parameterized by a single.
Yeah, I understand. But when you see the evolution of the
No,
string,
embedding comes later. I'm not talking about embedding.
yeah, that's all.
Is it correct? Like if you have evolution of something.
Yeah, but then you are considering embedding the string in some high-dimensional space. What is that mean? Embedding means you imagine that the string lives in a high-dimensional space. Therefore, now from a high-dimensional perspective, if you have to locate the string, you need to parameters.
Basically, you're saying that you can have a function which would have feed each point on a high dimension. This is the string. But then what's the string? You are talking about a function which will each point would be corresponding to some point of string. What's a string?
Okay, so
String is just a set of fields.
Fields.
From action level, I guess that is the best answer. So, just to answer your question, I am writing the action. That's I guess this is the best answer. So sigmas are the parameters on the string one sheet. So there are d fields. So mu and u runs from 0 to d 0 to d. So there are d fields you are considering. So this action is for the d.
Is this somehow related to the Nambu-Goto action?
Yes, it's a polynomial. It is actually equivalent to number. So I think it is better to consider
The spring is a
D fields. So x are the coordinates on the field. So x mu are functions of sigma. And there are two parameters, right? So sigma is like sigma 1 and sigma 2. One is like time like, one is space. So one measures the time like direction in the string wall sigma, and the space. That is, I think, the best mathematical answer. You see string as embedded in some external hand. So here the target space is Minkowski. So in Minkowski space, you have E fields, and this is like a free scalar field.
by sigma you mean a sigma vector.
Yeah, sigma is sigma 1 and sigma 2 parameters. So I think this is the best mathematical answer. So now non-relative string, classical string. So this is of course not the reality of string. String theory, this is relative string. This one. So this is very toy model. So this is just a string on guitars. Everybody knows. So suppose this is a string, and length of the string you assume is A. Two dimension. Now, do you know this equation of motion of the string? It is class 2 level thing. Everybody knows this equation? It is just wave equation on the string. Standard. Everybody knows, right? I am not here. So this is the equation of motion. But we want to derive that from an action. And also there are two parameters you can see. One is mu0 is the mass density of the string, and T0 is the tension. So now, how many of you know Lagrangian and don't Lagrangian action? Everybody knows.
ASMS first.
Okay, so I just give very 2 minutes. What is I? So suppose there is a particle in 3 dimensions. Not 3 dimensions. So what is the equation of motion? This is okay, right? This is the equation of motion. Now you need to devise a very elegant way to derive this equation is the action principle. So what you do, you define some object which is a function of what you do, you define it to be kinetic energy minus potential energy. That is, so kinetic energy of a particle is simply minus some potential. Now, if you can define the action to be the time integral of this scale from some initial configuration to final configuration. Means there is a particle that is going. So this is a string. And to okay, so So there can be many possible paths connecting these two functions. So you extremize this action to get path which minimizes the. So if you do that, you get something known as the Euler-Lagrange equation, which is basically this one. If you put that L here, you will get. So this is a way to. Means if you know the action of any system, you know everything of that system. That's all. Okay, so I want to write the action for the non-relative state. So same procedure, we need to write the kinetic energy minus potential. So it is a non-relative system. So what is the kinetic energy? It is like half mv square. Now what is half mv square for there? So it is integration from 0 to n. Half is there. Mu means mu 0 here. And v is okay, right? So this is mu 0 dx is the mass of the infinitesimal piece of the string. This is the velocity, and you have integrated over the volume. And how do you get the potential energy? Potential energy is basically the work done. Right? So here, at dm you can calculate. So basically, this is the initial configuration, you say like dx. And when the string vibrates, it acquires a dy also. So dm is basically the root of x square dy square minus.
I have a question. Here, we are instituting the binary energy part. U naught dx is kind of the mass.
Yes, we not dx is the mass, I'm saying. Yeah, it is the mass minus the velocity. And you are integrating over the all this.
Yeah,
All the
we are taking the length of around the length of the system and the velocity of.
yes. So this is a transverse velocity.
Yeah.
There is a transverse velocity.
But there can also be like.
Longitudinal.
Yeah.
Yeah, I will come to that. Why longitudinal as okay. So I am only considering the transverse velocity. Okay. So if you just remove dx from here, it will stay common. You will get something like this. Now, sorry.
When you are considering the U naught dx, you are considering a straight stream. Or by this straight stream.
Doesn't matter.
But U naught
You are integrating over it. This is just infinitesimal piece.
yeah, but only in the x direction.
Yeah.
The straight stream.
Okay, so just you use just Taylor expansion. Okay. This is approximately. Is okay, right? So what is the potential energy? Potential is energy is nothing but integration 0 to half. Now you have kinetic energy and potential energy. That's this thing is there. So Lagrangian. shorthand, so everything is. So this is the Lagrangian, and we can write the action. What should be time integral of this? There will be two integrals. So what I write, this bracket I write as cardinal. This is function of. So this cardinal is called the Lagrangian density. This is the setting. Do you have any question?
It's not comment. Weight is not a function of the x and y.
I will come to the symmetry. Okay. Now you need to just vary the action and set it to 0 to get the equation of motion. So right, vary the action or you will. Okay. Just write. You just take the delta variation of the action and now you apply bypass to collect the terms. What do you get? I write. So you will basically get 3 terms. This is 1 term. There are 2 terms. Okay. So you need to set that delta is to be 0 to get the equation of motion. Then you need to put all the terms separately 0. So if you set it to be 0, you get the equation of motion. This is the equation of motion we have written earlier. Now how to set 0 these boundary terms? So one thing I missed when I talked about the Lagrangian. So you need to put two boundary conditions. That is, you have to put these two boundaries with the variation of the 8 points or 60. Here also we are doing the same. So you need to apply this condition. So if we apply that, this term vanishes. So only term is remaining this one. Only term is remaining this term, so I am writing this term again. This is the most important term in the action, and from this term you will get all the open string force terms. This is very much important. What happens in the Poisson? First term vanishes, right? For the special for the initial and final configuration is fixed. It should be a delta of delta is there. So the first. Okay, so first term vanishes, means first boundary term vanishes for that boundary condition, and now this is the most important term. So it is better to write it in expanded form. So what will be that? So this is the expanded, I just expanded. Now you have to specify some boundary condition in top of them, in addition to this, you have to vanish, you have to make this vanish. So there can be many possibilities. And for that, now I just define x0 to be x0 or so this basically denotes the endpoint. So first one boundary condition can be Newman. Newman boundary condition. That is, you set so if you set this derivative of y to be 0 with respect to x at the endpoint, this term is x, right? So this is the Newman boundary condition, and for this boundary condition, delta y at the endpoints can be anything. So these are free endpoint conditions. So the string, open string is free. So this is called open string. So this actually gives you also, this is called NN string. At the both endpoint you put even one. This is called NN string.
Also, you can put different boundaries,
Yes.
different times as well.
I will come. There are many boundary conditions. So in string theory, your boundary condition determine everything. What you say. Now second condition can be delete. So which the boundary condition is the fixing the delta y at the moment. This also means that the endpoints are fixed at the boundary, so there is no velocity. So the same thing is, we say that the time derivative at the endpoint. So Newman is the spatial derivative 0 and this is the time. And this is a fixed open string. This is a fixed open string. And this is also called GC. In the both endpoint you put digital on. And there can be mixed also, right? So I will come to that in the next part. So there can be ND or DN strings also. These are also open strings. One point is fixed, another is fixed.
ND and DN are different.
Same thing I do. So we can actually for x equal to 0 you can put Newman. And there is another kind of boundary condition. This is period. What is periodic boundary condition? To together put this equal. So this is nothing but you identified 0 to b. These 2 points are same, so this is a closed. So you can see that the last term of the string acting the boundary term will determine what kind of string. Now, what are the symmetries of the Lagrangian? You don't need that. So Lagrangian is dependent on these 2. It is time derivative of y and spatial derivative. So there is no explicit dependence on x, y, and so there is no dependence on t. So somehow energy is conserved. No dependence on y means momentum around the y. But will it be conserved? It depends on the boundary conditions as well.
But you assume that there is no longitudinal motion, so Px is already zero.
It can have longitudinal motion, but it is not of our interest. So actually, I will not talk about this. I will just talk about this. Okay. Now, if you just substitute, so what will be the energy? Energy will be E plus B, right? So this is just the x. Now I will not do the steps, so you just do the math. Okay, you just substitute the equation of motion, use the equation of motion sum and reduce it to the form, then reduce it to the form. And y prime means the dxy and y dot means dy. So you can see that energy is always conserved no matter what boundary condition you use. Del x. Del xy, del u. Product. So no matter what boundary condition you use, energy is always conserved. Oh, sorry. This is d. You have to take another value. So you can say this is always x. So energy is always important. Now coming the Py, momentum Py, that is the transverse momentum. So what is the momentum? In mass times velocity, right? So mass is something like mu dx times velocity. Now we integrate. You do the steps and it is very easy to calculate. So you will get something. Now the interesting part is this. So you can see only for periodic boundary condition with those strings and the Newman boundary condition, this momentum is not for Dirichlet strings. Okay. So this was an open-ended question long back, and Polyakov actually means string theory is first of all they do not consider the Dirichlet string as a momentum is a concept. Then Polyakov suggested that the strings are like waves, means breaks. That is the main thing, and the momentum of the string is transferred to the deep in order to convert. That's why branes are also called deep. dim DDC. So the open DDC strings are connected to events and the momentum is conserved. As brains are also dynamical objects, so it will absorb the momentum. So this is the thing, and the last part. Absorb the momentum. What does that mean? Then
Give some
yeah, you can give some effect, I guess.
Or it simply you have a say cardboard, that's a string to it. You get the string, the cardboard will move or something. There will be a local distance. That is what it means by absorbing the momentum transfer between the
That I understood. What
Can we
So
observe
the
it?
fields will tighten.
What is the order of this? What is the order of this?
Well, this is just a non-relativistic CIN. So I don't know what's the order of the momentum. Like we
How
have
we going to observe some effect like
it is same as the grid string. You just attach the string to the end point. So the actual thing is I said the relativistic quantum strings. There is much more sophisticated. This is same as the guitar string.
So one more thing. To take off the basically on the connections where the momentum is not connected, we don't have y in the Lagrange entry.
Why?
The y coordinate is not there in the Lagrange.
Not there in the Lagrange. We are getting yes. Yes, it depends on the boundary condition, what boundary condition you are choosing. So this is same as the string in the guitar. So these are fixed. So when you plug it, so there are some effects. So it should be strong. Strongly fixed. Okay. Now the last thing is non-relativistic string excitations. I will discuss. Somehow it will give us the derivative from close. Not. I mean, it is very toy thing. So the equation of motion is, so I will just briefly speak, I will not do the calculation. So you need to solve this equation subject to various boundary conditions. So you will put an answer and separate the time dependence. Okay. So if you now substitute this here, the time dependence will not just there will be some differential equation in x. That will be very similar to the harmonic oscillator problem. Where omega square is equal to now, what is the general solution? You know, general solution is A cos omega x plus B sin omega. Right? And to calculate also y sin omega. You know how to calculate y sin omega. Is also now you just apply the boundary conditions. That's it. So for DD string, it is both in you have divisional boundary condition that is y of 1. So this is like a quantum mechanics problem to solve the equation. So you will get the solution as something.
Some expression I'm not writing, but this is the chart. Now do the similar thing for NN. So NN we have to put this boundary condition. So you will get similar type of solution. Cos, you will get cos. And the same omega. Now for closed string you need to put the periodic boundary condition in y0 equal to y and this equal to this. Right. So you will get a solution which contains cos plus. And the interesting thing is that omega is yes, the idea is very small omega. So the interesting thing is this will be 2 times so 2 things you notice that there is one independent wave in the string for the open string, but in the closed string you have 2 independent waves as well as the frequency 2 times. So if somehow, so this is very vaguely speaking, so if somehow these are like spin 1 particles in the string because there are 2 independent waves. So this is very vague, this can be known. I'm just saying, we have just have a thing. So the closed string expressions are like spin.
Can a closed string break into two open strings?
So is that there is an external force?
Everything is just finger interacting.
I don't know. So this is one nice thing that you can know. Now what happens for alien game? The last one. If you consider this, so you have to put one end to the Newman boundary condition, other end to the Dirichlet. So what we will actually get? We get something like sine. For one case we will get sine, for one case we will get cos, or ambient game. We will use the and the omega you will get what is some it is not sorry for any I think you will get sine for any also. So you can see that for Indian DXT it is like there is only one independent wave you can get and the frequencies are like half integral kind of frequency. So these some two waves are like 30. That's the equation.
But you did not answer why you need to start with not the samples.
Oh, okay. So to answer this question, actually I have to use a relative strings. Usually in relative strings, the longitudinal motion is not necessarily not important. In some case choice you can remove that longitudinal. There is called so actually I was discussing sigma 1, sigma 2 parameters. So it is like something like tau with sigma. Very time like direction, this is very special. In string also.
translation symmetry around one of those.
Right?
So is there a translation symmetry in tau sigma?
Symmetry. Yeah. Yeah, there is a translation. The action will not depend on the coordinates. Tau and sigma.
But in actually we get
Is that why you can sort of gauge up this one way of that's it related?
but energy can still get an energy.
So what the picture is, so I am just giving you a brief picture. Suppose this is X1, this is not all the other columns. And this is time. So, and open color. So, and open string will follow. So this is called the wall string. It is a two-dimensional surface in the space, and a closed string will follow something like this. So a closed string will follow a cylindrical shape. So this is topologically equivalent to string. So this is the evolution of the open and closed string in the space. And what you do, you define some coordinates. One you call like sigma. This is on the wall string. You are defining the parameters. Now what you can do to choose, there is a gate choice, you set it to be 6. This is the gate choice. And what you do, you take sigma to be perpendicular to each point. If this is the tau direction, sigma is like this. So in that way, only one velocity is there. Only v perpendicular is there. V longitudinal is there. Right.
So basically we are kind of working the way of the string.
Yeah. So this is a particular range. So this is a way of saying, so there are technically so this is called a static range.
Does anyone else have any question?
Yeah, this is now the question answer.
If not, let's kind of bigger ones.
Was it boring or yes?
Yes, sir.
Means
I will share this.